In the grand, chaotic ballet of the cosmos, nature almost never draws a straight line. It prefers the glorious swirling curves of a spiral galaxy, the gentle arc of an orbit, the turbulent, unpredictable billows of a nebula. It is a universe built on ellipses, spheres, and glorious, untamed fractal patterns. Geometry, in its purest, most rigid form, has long been considered the exclusive domain of life, of intelligence, the signature of a mind at work. So what are we to make of a place where the universe seems to violate its own deepest artistic impulse? A place where chaos has inexplicably surrendered to order, giving birth to an object so mathematically perfect, so profoundly unnatural, it feels like a declaration. It waits for us in the cold, outer darkness of our own solar system, a geometric ghost haunting the top of a world. There, suspended in the perpetual twilight of Saturn's North Pole, is an impossibly perfect hexagon. This is no trick of light, no fleeting illusion. It is a storm system, a weather pattern of such colossal scale and bizarre precision that it defies our every intuition about how planets are supposed to behave. You must picture its immensity to truly grasp the paradox. This is not a quaint atmospheric quirk. It is a structure twice the diameter of our own planet. You could drop two Earths side by side into its yawning interior with room to spare. Its 6 straight sides, each one longer than the diameter of the Earth itself, are not solid walls but terrifyingly fast rivers of wind. A jet stream moving at over 300 miles per hour forms a hypersonic fence, corralling a maelstrom of violent, churning clouds within its perfect geometric boundary. At its heart, a colossal hurricane, a permanent vortex, stares out into space like a great unblinking eye. For centuries, perhaps for millennia, this cosmic stop sign has been spinning, a testament to a force we have yet to comprehend. It presents a profound challenge, not merely to our understanding of weather, but to the fundamental laws of fluid dynamics that govern everything from a cream stirred into coffee to the formation of stars. This is a scientific detective story of the highest order, and its first clue was a faint ghostly image, a whisper from the void. Our first encounter with this enigma came in the early 1980s. The Voyager spacecraft, humanity's intrepid emissaries to the outer solar system, were executing their grand tour, a spectacular, once-in-a-lifetime planetary alignment. They were marvels of engineering, compact vessels packed with instruments, flung from Earth on a gravitational slingshot course that would take them past Jupiter and then onward to the majestic ringed world of Saturn. For the scientists at the Jet Propulsion Laboratory, it was the culmination of decades of work. Years of calculations, simulations, and hopes were pinned on these fleeting flybys. Data, encoded as faint radio signals, trickled back across nearly 1 billion miles of empty space, each bit of information a precious gem painstakingly collected. As Voyager 1 and then Voyager 2 swept past Saturn, they painted a portrait of a world more complex and dynamic than we had ever imagined. They revealed the intricate, shimmering structure of the rings, discovered new moons, and mapped the planet's turbulent, butterscotch-coloured atmosphere. And then they saw it. Among the thousands of images sent back, a few frames captured the planet's North Pole. The pictures were grainy, low resolution by today's standards, a series of black and white snapshots taken from a vast distance. But even through the digital noise, a pattern emerged. It was subtle, barely discernible amidst the swirling cloud bands, but it was unmistakably there. 3 straight connected lines forming part of a larger polygon. Scientists were baffled. They stitched the images together, enhanced the contrast, and stared in disbelief. Storms were supposed to be round. Vortices were supposed to be circular, or at best, oval. The physics of rotating fluids demanded it. A straight line, let alone 6 of them forming a perfect hexagon, seemed to mock the laws of nature. Was it an artifact, some strange glitch in the camera's imaging system? Or was it real? The data was too limited, the glimpse too brief. Voyager, its mission at Saturn complete, was already moving on, its trajectory carrying it inexorably toward Uranus, Neptune, and eventually the cold, silent frontier of interstellar space. It could not turn back. It could not take a second look. For decades, the hexagon ceased to exist as an observable reality. It became a scientific legend, a ghost in the machine. The problem was Saturn's own majestic tilt. Just like Earth, the gas giant has seasons, but on an entirely different timescale. A single Saturnian year, one slow lap around the Sun, takes nearly 30 of our Earth years to complete. As Voyager sped away, the planet's northern hemisphere was tilting away from the Sun, plunging the North Pole into a long, dark polar winter that would last for 15 years. For 1.5 terrestrial decades, the pole where the anomaly had been seen was shrouded in absolute darkness, hidden from the prying eyes of our telescopes on and around Earth. The mystery was forced into hibernation. Planetary scientists debated its existence in academic papers and conferences. Some proposed it was a transient wave pattern, a fluke that had dissipated moments after it was seen. Others clung to the belief that it was a stable, long-lived feature, a tantalizing hint that the atmospheres of gas giants harbored physics far stranger than we knew. But without evidence, it remained a tantalizing, unprovable hypothesis. The hexagon had become a question mark hanging in the void, waiting patiently for humanity's return. That return came in the form of one of the most ambitious and magnificent robotic explorers ever built, the Cassini-Huygens mission. Launched in 1997, Cassini was a school bus-sized nuclear-powered spacecraft, a mobile laboratory bristling with a sophisticated suite of 12 scientific instruments. Its journey to Saturn was a long and looping odyssey, taking 7 years to navigate the gravitational crosscurrents of the inner solar system, before it could finally break into orbit around the ringed planet in 2004. Its arrival marked the dawn of a new era. For the first time, we wouldn't just be flying by, we would be staying. Cassini was destined to become an artificial moon of Saturn, spending over a decade in a complex dance of orbits, weaving through the rings, buzzing past icy moons, and scrutinizing the planet in unprecedented detail. And on its long list of scientific objectives, one mystery loomed large, the case of the polar hexagon. Still, the universe demanded patience. When Cassini first arrived, the long northern winter was not yet over. The pole remained stubbornly hidden in shadow. For years, the spacecraft performed its other duties, revolutionizing our understanding of the Moon, Titan's methane seas, and Enceladus's subsurface ocean. All the while, the team waited, tracking Saturn's slow, deliberate tilt back toward the Sun. They used Cassini's infrared instruments, which could pierce the darkness and see heat rather than visible light, to get their first new glimpses. What they saw sent a jolt of excitement through the scientific community. The thermal maps showed a distinct hexagonal boundary, a clear temperature difference between the air inside and outside this massive shape. The ghost was still there, a warm spectre haunting the frigid dark pole. It had survived the long winter. It was not a fleeting phenomenon, it was a permanent piece of planetary architecture. Then, finally, in 2009, the seasons turned. Sunlight, for the first time in 15 years, began to grace the northernmost latitudes. Cassini's powerful cameras were turned northward, and the world held its breath. The images that came back were breathtaking. There, in stunning high-resolution clarity, was the hexagon. It was not a subtle, ghostly pattern anymore. It was a stark, undeniable, razor-sharp feature etched onto the face of the planet. The perfect geometry was terrifying in its precision. The 6 sides were flawlessly straight, the angles between them seemingly exact. The entire structure rotated in perfect lockstep with Saturn's own deep interior, a vast, spinning carousel of clouds. It was as if a giant cosmic artist had used a protractor on a canvas larger than a world. Cassini's long vigil revealed even more strangeness. As the northern hemisphere moved from the darkness of winter into the light of spring and then the full glare of summer, the hexagon began to change colour. The hazy, deep blue hues of winter gradually gave way to a rich, golden yellow. This transformation suggested a complex photochemistry at play, with sunlight interacting with atmospheric compounds, or smog, that were trapped and concentrated within the hexagonal jet stream. The storm wasn't just a physical barrier, it was a self-contained atmospheric terrarium, an isolated chemical laboratory the size of a planet, brewing its own unique seasonal atmosphere. And at its very centre, the mystery only deepened. Cassini's cameras zoomed in on the North Pole itself, revealing the hurricane that served as the hexagon's axle. This polar vortex was a storm in its own right, 50 times larger than a typical hurricane on Earth, with an eye over 1,000 miles across. Winds at its outer edge screamed at more than 330 miles per hour, yet in its tranquil centre, the clouds were descending, diving deep into the planet's interior. It was a monstrous atmospheric drain, pulling the sky down into the abyss. But unlike the hexagon that contained it, the polar vortex was defiantly circular. This created an even more bewildering puzzle, a round storm sitting inside a hexagonal storm. How could two such different dynamic systems coexist so closely and so stably? How could the chaotic, spiralling energy of the central hurricane be contained by the rigid, linear fence of the hexagon's jet stream? It was a violation of every computer model we had ever designed for planetary atmospheres. This is the core of the enigma, the reason the hexagon continues to haunt the dreams of planetary scientists. Fluid dynamics, the science that governs the flow of liquids and gases, is a field we think we understand well. On Earth, it gives us the beautiful, swirling spirals of hurricanes and the puffy, chaotic shapes of cumulus clouds. When you introduce rotation, as you must on a rapidly spinning planet like Saturn, you get vortices. You get ovals, like Jupiter's Great Red Spot. You get circles. You never ever get a hexagon. The forces involved simply don't produce straight lines or sharp corners. A stable, standing wave pattern might form with multiple lobes, but it should be wavy and sinuous, not angular. The hexagon's sharp 60-degree corners are a physical impossibility by our current understanding, yet they persist, year after year, decade after decade. It's as if you threw a rock into a pond and instead of circular ripples it produced a cascade of perfect expanding squares. You would be forced to question not the rock, but your understanding of water itself. We are confronted with a similar crisis of understanding. The hexagon is not just a weather report from a distant world, it is a direct challenge to our textbooks. It forces us to ask terrifyingly fundamental questions. What force, what hidden mechanism, is powerful enough to grab a planet-spanning jet stream and bend it into 6 straight lines? What is the engine that has powered this geometric monstrosity for untold centuries? Could its existence be tied to something deep beneath the clouds, a clue to the exotic physics at play in Saturn's crushing interior, where pressures are so great that hydrogen becomes a liquid metal? The hexagon feels less like a storm, and more like the visible manifestation of a much deeper, hidden structure, a gravitational gyroscope or a resonant wave pattern echoing up from the planet's very core. It is a lock for which we have no key, a message written in a language we have not yet learned to read. Solving this puzzle is more than an academic exercise. It is a quest to understand the vast range of possibilities that nature allows. If such a structure can form here, on a planet we can study in detail, what other impossible forms might exist on the thousands of gas giants we are now discovering around other stars? To find the answer, we must journey from the farthest reaches of the solar system to laboratories right here on Earth, where scientists are spinning tanks of water, desperately trying to coax a miniature hexagon into existence. We must dive into the digital realm of supercomputers, where complex simulations struggle and fail to replicate Saturn's masterpiece. And we must look back at the data, at the legacy of the Cassini mission, searching for the subtle clues we may have missed. The story of the hexagon is the story of a perfect mystery, a cosmic anomaly that beckons us forward, promising that just when we think we have grasped the rules of the universe, it reveals a new and beautiful exception. What does it truly mean to see a world? Is it the simple act of light striking an eye or something deeper? For centuries our view of Saturn was an act of profound imagination, a conversation with a distant point of light conducted across an almost unimaginable gulf of darkness and silence. When Galileo Galilei first aimed his crude spyglass at that wandering star in 1610, he wasn't prepared for what he saw. He didn't see a planet as we know it, a perfect sphere hanging in the void. He saw something strange, a world with ears. Or perhaps, he thought, a planet flanked by two loyal companions, two lesser moons that refused to move away. He sketched his confusion, his drawings revealing a perplexing trinity, a central globe with two mysterious appendages. For years, the truth of Saturn remained a blurry, frustrating enigma, a riddle whispered by an imperfect lens. It was a world wearing a mask, and humanity could only guess at the face hidden beneath. It would take another half-century, and a far more powerful telescope in the hands of Dutch astronomer Christian Huygens for the mask to finally slip. In 1655, the ears resolved themselves. They were not moons, they were not appendages. They were a ring, a luminous, impossibly thin structure suspended in space, encircling the planet without touching it. The discovery was breathtaking. It was absurd. It violated every expectation of how a world should be. In that moment, Saturn was redefined forever. It ceased to be just another planet. It became the jewel of the solar system, an object of sublime and singular beauty. And for the next 300 years, that is precisely what it remained. Our gaze and our science became utterly mesmerized by this celestial halo. The rings were a performance of such cosmic grandeur that they stole the show completely. We studied their composition, debated their origin, and marveled at their intricate grooved structure. They were a gravitational masterpiece, a testament to the elegant and sometimes bizarre physics that governed our solar system. But this singular focus, this obsession with the planet's magnificent ornament, came at a cost. It distracted us. While we were looking at the rings, we weren't truly looking at the world they encircled. From Earth, even with the finest telescopes that followed Huygens, the planet itself was a subtle canvas of muted colours. We could discern faint bands of cream, butterscotch, and pale gold stretching across its equator, hints of a dynamic atmosphere. We saw the planet's noticeable flattening, its poles squashed, and its equator bulging from its dizzyingly fast rotation, a day on Saturn lasting a mere 10.5 hours. This rapid spin, we knew, must be a powerful engine for weather, stretching clouds into planet-circling jet streams. Yet the details remained tantalizingly out of reach, smeared into obscurity by the turbulent ocean of Earth's own atmosphere and the sheer, humbling distance. Saturn was a soft watercolour world, its face a gentle abstraction, its poles, the very regions that sit at the apex of its rotational axis, were reduced to little more than smudges of light, their features completely lost to us. We saw the frame, but the portrait remained a mystery. We admired the crown, but we knew nothing of the mind of the monarch who wore it. Before we could send our first robotic emissaries into the outer dark, our understanding of worlds like Saturn was built not on observation, but on pure theory, on the grand architecture of physics. Scientists of the 19th and early 20th centuries were celestial architects, trying to blueprint a world they could not visit. They began with the principles they understood from Earth. They knew about heat and convection, the simple, elegant dance where warm fluid rises and cool fluid sinks. On Earth, this dance is powered by the sun, which unevenly heats our planet's surface, its oceans and continents. This differential heating, combined with our planet's spin, creates the Coriolis effect, a ghostly force that deflects moving air and water, twisting weather systems into the familiar spirals of hurricanes and cyclones. Our weather, in essence, is a thin, fragile film of activity stretched over a solid rocky foundation, moderated by vast, stabilizing oceans. But what would happen if you took those same physical laws and applied them to a planet like Saturn? A planet with no solid surface to stand on. A world that is, for all practical purposes, an almost bottomless ocean of gas. Where on Earth you have rock and water, on Saturn you have hydrogen and helium, compressed by staggering pressures into an exotic liquid metallic state deep within its core. This was the first great conceptual leap. Saturn's weather wasn't just a skin-deep phenomenon, it was the expression of the planet's very soul, a storm system that could extend downwards for thousands of kilometres, unhindered by the friction of a solid ground. There were no mountains to break the winds, no continents to disrupt the flow. There was only the relentless three-dimensional churning of a world-spanning atmosphere. Furthermore, scientists began to suspect that the Sun was not the primary driver of this colossal weather engine. Saturn is 10 times farther from the Sun than Earth is. Solar energy reaching its cloud tops is feeble, nearly 100 times weaker than what we feel on a sunny day. The sunlight arriving there is a pale, ethereal glow, barely enough to warm the upper atmosphere. No, the real engine had to lie within. Theory predicted that Saturn, like its larger sibling Jupiter, was still radiating heat left over from its violent formation 4.5 billion years ago. It was a world slowly cooling, its interior a vast reservoir of primordial energy. This internal heat, bubbling up from the crushing depths, would create convection currents on a scale that dwarfed anything on Earth. Imagine titanic columns of hot gas, broader than entire continents, rising through the atmosphere, cooling, and then sinking back into the abyss. This vertical motion, this planetary breathing would be the furnace. And then there was the spin. Saturn's furious 10.5-hour day injects an astonishing amount of angular momentum into its atmosphere. The Coriolis force on such a rapidly rotating fluid world would be monstrously powerful. It wouldn't just gently deflect winds, it would violently shear them, organising the rising and falling convection currents into the distinct parallel bands we could faintly see from Earth. Theory painted a picture of a world dominated by ferocious globe-circling jet streams, rivers of wind moving at speeds that would shatter any terrestrial scale. Where Earth's fastest jet streams might reach 400 km per hour, the winds on Saturn were predicted to scream past at over 1,500 km per hour. This wasn't weather as we knew it. This was a vision of fluid dynamics operating at its most extreme, a symphony of physics played out on an unimaginable scale. The only real-world example we had of a truly persistent storm system in such an environment was Jupiter's Great Red Spot. This crimson eye, an anticyclone so vast it could swallow the Earth whole, had been raging for centuries. It was a testament to the stability of storms on a gas giant, a self-sustaining vortex that, lacking the friction of a solid surface to slow it down, could seemingly last forever. It was a gravitational gyroscope, a spinning top of gas that simply refused to stop. So the question for Saturn was not if such colossal storms could exist, but what form they would take on a world with different properties, a world that was colder, less dense, and with even faster winds than Jupiter. The poles, in particular, were a region of intense theoretical interest. On any spinning sphere, the pole is a unique point. It is the calm, unwavering axis around which everything else revolves. All the planet's churning energy, all those ferocious east-west jet streams, would have to converge and interact at the poles in some fashion. What would happen at that nexus? Would it be a region of serene calm, an eye in the global hurricane? Or would it be a place of unparalleled violence, a vortex where the planet's atmospheric energy spiraled into a single terrifying maelstrom? For generations, these questions remained in the realm of chalkboards and complex equations. Saturn was a theoretical playground, a world of thought experiments, and then, in the late summer of 1977, humanity began to send its answer. 2 spacecraft, Voyager 1 and Voyager 2, left our world on a trajectory that would take them on a grand tour of the outer solar system. They were marvels of their time, compact vehicles packed with instruments designed to see, hear and feel the cosmos in ways we never could from Earth. On their shoulders rested the hopes of an entire generation of scientists. For years they flew, silent pilgrims crossing the vast, empty expanse between the planets. They passed Jupiter, revolutionizing our understanding of its stormy atmosphere and discovering its faint dusty ring and volcanic moon, Io. And then they set their sights on the ringed planet itself. In November of 1980, Voyager 1 made its closest approach. It was a fleeting, high-speed encounter. In the mission control rooms at the Jet Propulsion Laboratory, an anxious quiet settled. For years they had planned for this moment. They had calculated every trajectory, every command sequence. Now, all they could do was wait as the spacecraft, over 1 billion kilometers away, executed its instructions. The data began to trickle back across the solar system, a fragile stream of radio waves carrying pictures of a world no human had ever seen up close. The first images were, as expected, glorious. The rings resolved into a breathtaking tapestry of thousands of individual ringlets, with strange dark spokes that seemed to defy the laws of orbital mechanics. The planet's atmosphere was a stunning panorama of subtle flowing bands, punctuated by occasional storms and eddies. It was more beautiful and more complex than anyone had dared to imagine. The primary mission objectives were to study the rings, the planet's equatorial regions and its largest moon, Titan. The poles were a secondary target, difficult to image during a high-speed flyby. The spacecraft's trajectory meant it could only get an oblique sideways glance at the planet's northern latitudes, which were then shrouded in the long, cold darkness of winter. The cameras, remarkable for their day, were still products of 1970s technology. They were essentially sophisticated television cameras, recording images onto magnetic tape, which were then slowly played back and transmitted to Earth. The resolution, by modern standards, was low. Yet, as the team processed the images from the northern polar region, something began to emerge from the digital noise. Something that didn't make sense. It wasn't a swirl, it wasn't a circle, it was a hint of straight lines. Among the grainy black and white photographs of the North Pole, there was a feature that seemed to defy the fluid, curving nature of a weather. It was a dark, shadowy shape, and it appeared to have corners. The scientists were baffled. At first, they dismissed it as a processing artifact, a glitch in the software that pieced together the individual image frames. They reran the data. The shape was still there. It looked like a polygon, a figure of impossible geometry carved into the planet's cloud tops. But the images were low contrast, taken at a poor angle and stitched together from multiple passes. It was like trying to identify a person from a great distance, through a thick fog. You might see a suggestion of a shape, a ghost of a form, but you couldn't be sure. Was it one large, coherent structure, or was it just a chance alignment of several smaller, disconnected clouds that created the illusion of a pattern? 9 months later, in August of 1981, Voyager 2 flew by. It too caught a fleeting, angled glimpse of the North Pole, and again through the haze of the data, the same apparition appeared. The strange, angular feature was still there, a whisper of impossible geometry at the top of the world. It was a tantalizing clue, but it was far from proof. The evidence was ambiguous, the images too blurry to offer any definitive answers. The flybys had happened so quickly, and the discovery was so unexpected, that there was no opportunity to stop and take a longer, more careful look. The Voyager spacecraft were moving on, their trajectories already flinging them towards Uranus, Neptune, and eventually the cold, dark frontier of interstellar space. They could not turn back. They left us with a profound and perplexing mystery. For centuries we had been blind to Saturn's face, seeing only its magnificent rings. Now our first robotic eyes had given us a glimpse, only to reveal a riddle more baffling than we could have ever conceived. Was there truly a colossal, six-sided storm raging at Saturn's North Pole? A hurricane the size of 2 Earths, bounded by straight lines and sharp corners, defying the fundamental physics of fluid dynamics? Or were we seeing a phantom, a trick of light and shadow in the clouds of a distant world? The Voyager mission had opened the door to Saturn, but the view through that door was murky, indistinct. We had found a puzzle box, but the key to unlock it was still missing. To solve this mystery, we would need to do more than just fly past. We would need to return. We would need to stay. We would need to become a part of Saturn's world, a sentinel in orbit, to watch and wait for the planet to finally give up its most extraordinary secret. For 2 long decades, the ghost haunted our archives. It was a whisper from the void, a fleeting pixelated shape glimpsed by the Voyager spacecraft as they slingshotted past Saturn, bound for the cold, dark frontiers of the solar system. A strange geometry, hinted at in the thermal glow of the planet's North Pole, then lost again to the darkness of a long winter's night. It was an anomaly, a question mark hanging over a world of rings and gas, a puzzle too brief, too blurry to solve. The scientific community catalogued it, debated it with academic caution, and then, with no new data to fuel the fire, largely set it aside. The universe, after all, is filled with unexplained phenomena. But on the 1st of July 2004, that quiet period of speculation ended forever. Humanity returned to Saturn, not for a passing salute, but to move in. This was the culmination of a journey that had spanned 7 years and covered more than 2 billion miles of interplanetary space. A sophisticated 12-instrument robotic explorer named Cassini, the most complex planetary probe ever built, was about to perform the most critical maneuver of its life. It was approaching the ringed giant at over 53,000 miles per hour, a speed at which a single, misplaced micrometeoroid could transform this multi-billion-dollar emissary into a cloud of shrapnel. There was no room for error. To become an artificial moon of Saturn, Cassini had to slam on the brakes, but in space there is no air to provide friction, no ground to grip. There is only the cold, unforgiving precision of orbital mechanics. The plan was audacious. A 96-minute engine burn, timed to the second, designed to bleed off just enough velocity for Saturn's immense gravity to reach out and finally capture the spacecraft. The burn had to happen at the perfect moment, in the perfect orientation, and for the perfect duration. Fire the engine for too long, and Cassini would slow too much, spiralling down into the planet's crushing atmosphere to be incinerated. Fire for too short a time, and it would fail to be captured, shooting past Saturn to become another piece of lost debris orbiting the Sun. Adding to the drama, the entire maneuver would take place on the far side of the planet, cutting off all radio contact with Earth. For that harrowing hour and a half, the mission controllers in California were utterly blind, passengers to a pre-programmed sequence of events that was unfolding nearly 1 billion miles away. They had sent their commands, checked their calculations 1,000 times over, and now all they could do was wait, listening to the static, hoping to hear the voice of their creation re-emerge from behind the giant. Imagine the tension in that room, a silence punctuated only by the hum of consoles, as the fate of a decade of work hung suspended in the void. The light from Saturn that they saw on their screens had left the planet 84 minutes earlier. By the time the signal was lost, the burn was already half over. They were watching history, helplessly lagging behind the event itself. Then, after an eternity of radio silence, a single spike of energy appeared on the monitors of the Deep Space Network. A carrier wave, a faint, triumphant tone broadcast across the solar system. Cassini was alive. It had survived the fiery ordeal. The engine had performed flawlessly. Humanity had a permanent outpost in the court of the Ringed King. The door to Saturn's deepest secrets had just been thrown wide open, and the first thing we would find waiting for us on the other side was an old ghost, now ready for its close-up. The true confrontation with the hexagon was about to begin. Even with Cassini in orbit, the mystery remained veiled. Saturn's northern hemisphere was still plunged in the deep perpetual twilight of its 15-year-long winter. The pole was a realm of profound darkness, invisible to conventional cameras that rely on reflected sunlight. If you were to look with your own eyes, you would see nothing but an endless, featureless black. But Cassini was not limited to human vision. It carried instruments that could perceive the universe in ways we cannot, seeing in wavelengths of light that are impassable to us. One of these instruments was the Visual and Infrared Mapping Spectrometer, or VIMS, a device capable of detecting the planet's own internal heat radiating out into space. In the cold darkness of the Saturnian winter, VIMS could see the weather. It could map the structure of the atmosphere not by what it reflected, but by what it was. The science teams pointed VIMS toward the North Pole, the location of Voyager's strange anomaly, and began to collect data. What came back was not a refinement of the old grainy images. It was a revelation so sharp, so geometrically perfect, that it sent a shockwave of disbelief through the planetary science community. There, glowing in the thermal infrared, was the hexagon. But it was no longer a smudge, no longer an ambiguous shape open to interpretation. It was a form of crystalline precision, a stop sign forged from atmospheric dynamics. The vertices were not rounded or indistinct. They were sharp, angular corners, as if drawn by a celestial architect. The 6 sides were not vaguely straight. They were lines of impossible linearity, each one longer than the diameter of the Earth itself. This was the moment of scientific whiplash. For decades, we'd been trained by observation and by theory to see planetary weather as a chaotic dance of curves and swirls. We expect spirals in our hurricanes, eddies in our currents, and undulating waves in our jet streams. Nature, especially in a fluid, gaseous environment like Saturn's atmosphere, abhors straight lines, and yet here was a meteorological structure that defied that fundamental rule on the most colossal scale imaginable. It was as if we had discovered a perfectly square hurricane on Earth. The initial reaction was not excitement, but a deep, unsettling confusion. The data had to be wrong. It was an artifact of the instrument, a glitch in the processing software, a trick of the viewing angle. Team after team recalibrated their tools, reran the data, and checked every line of code, desperately searching for the error that would make the universe make sense again. But there was no error. The hexagon was real. The data was irrefutable, and with every new pass Cassini made over the pole, the feature resolved itself with even more audacious clarity. It was a fixed pattern, a permanent fixture carved into the fabric of the planet, and its scale was simply mind-shattering. Try to wrap your mind around this structure. If you place a map of our own world inside it, the entire Earth, from the North Pole to the South, would fit comfortably within the central vortex alone. The hexagon itself is so vast that you could line up 4 Earths side by side, and they still wouldn't span its full width. Each of its 6 sides is a jet stream, a river of wind screaming through the upper atmosphere at over 300 miles per hour. These are not gentle breezes. They are atmospheric shears of unimaginable power, walls of moving gas that define the perimeter of this impossible shape. To fly a spacecraft along just one of its 6 sides would be a journey of more than 9,000 miles. A commercial airliner, if it could survive the turbulence, would take nearly a full day to traverse that single segment. This discovery was more than just a new weather pattern. It was a direct assault on our understanding of fluid dynamics. How could such a structure form in a spinning gaseous sphere? In a laboratory on Earth, physicists can create polygonal shapes in swirling fluids, but those are delicate, small-scale phenomena that require finely tuned conditions and exist for only fleeting moments. Saturn's hexagon, however, was a beast of an entirely different nature. It wasn't a transient flicker in a petri dish. It was a planetary scale structure, older than any human civilization and inexplicably, almost violently stable. It rotates with a period of 10 hours, 39 minutes and 24 seconds, a rotational speed so precise and unwavering that scientists began to use it as the most reliable measure of Saturn's deep interior rotation, a kind of gravitational gyroscope linking the surface weather to the very core of the planet. For years, the world of Saturn's North Pole remained a realm of 2 realities. There was the infrared reality captured by VIMS, which showed this vibrant, glowing, perfectly geometric storm system in stunning detail. And then there was the visual reality seen by Cassini's main imaging cameras, which showed only blackness. The scientists knew this colossal structure was there, churning away in the winter dark. They could measure its temperature, map its winds, and track its perfect rotation. They could feel its presence in the data, a sleeping giant whose form they knew intimately but whose face they had never seen. A profound sense of anticipation began to build within the mission team, a slow burning impatience for the seasons to turn. They were waiting for the sun. Saturn's orbit around the sun takes nearly 30 Earth years to complete, meaning its seasons unfold with an epic slowness. Winter in the northern hemisphere had begun long before Cassini's arrival, and for the first 5 years of the mission, the pole remained cloaked in shadow. But slowly, painstakingly, the planet's axial tilt began to shift relative to the sun. The long night was coming to an end. The date circled on every mission planner's calendar was August 2009. This was the time of the Saturnian equinox, the moment when the sun would shine directly on the planet's equator, and for the first time in 15 years, its rays would begin to creep northwards, inching across the high latitudes. It would be a new dawn, not just for Saturn, but for our understanding of it. The science teams began to prepare, aiming Cassini's powerful cameras at the still dark region, ready to capture the very first photons of sunlight to strike the hexagon in a generation. As the light finally returned, what it revealed was even more bizarre, more alien, and more beautiful than anyone had dared to imagine. The first visible light images trickled back to Earth, and they were breathtaking. The hexagon was there, exactly as the infrared data had predicted, its stark geometric perfection now laid bare for all to see. But it wasn't just a shape, it was a place of profound and dynamic colour. In the early spring sunlight, the entire region within the hexagon was cast in a deep, mesmerising, almost ethereal shade of azure blue. The surrounding atmosphere outside the six-sided barrier was the familiar pale butterscotch gold of Saturn. The hexagon acted as a perfect container, a boundary that seemed to hold back the golden clouds, creating a stark, painterly contrast between the blue interior and the yellow exterior. Scientists were baffled anew. Why blue? The initial hypothesis was that the long winter had allowed aerosols and other haze particles to settle out of the upper atmosphere inside the hexagon, leaving it clearer than the rest of the planet. This cleaner air scattered sunlight more efficiently at shorter wavelengths, a phenomenon similar to the Rayleigh scattering that makes Earth's sky blue. The hexagon's jet stream walls were acting as a barrier, an atmospheric fence preventing the yellowish haze from the rest of the planet from mixing into this purified polar air. It was a spectacular theory, but Saturn was not done with its surprises. As the northern spring advanced into summer over the next several years, Cassini watched, mesmerised, as the hexagon began to change. The beautiful, tranquil blue slowly warmed, shifting in colour. It morphed into shades of green, then yellow, and by the time northern summer solstice arrived in 2017, the entire interior of the hexagon had transformed into a rich, deep golden hue, almost perfectly matching the colour of the atmosphere outside it. The storm was a chameleon, changing its appearance with the seasons in a way never before witnessed anywhere in the solar system. The sheer audacity of this object, its geometric stability, its titanic scale, and now its seasonal colour shifting, pushed the scientific community into a state of profound reassessment. The hexagon was not just a weather pattern, it was a self-contained, self-regulating ecosystem of atmospheric chemistry and dynamics, a world within a world governed by laws we had yet to decipher. At its very centre, Cassini's cameras resolved a swirling vortex, a polar hurricane locked in the heart of the geometry. This central storm was itself over 1,000 miles wide, with an eye wall where winds reached speeds of over 330 miles per hour, twice as fast as a Category 5 hurricane on Earth. It was a storm within a storm, a maelstrom nested inside a perfect polygon. The data pouring back from Cassini was an avalanche, a treasure trove of clues that was as overwhelming as it was enlightening. Every new image and every new dataset deepened the mystery, while simultaneously providing the very tools needed to solve it. The conventional models of how planetary atmospheres should behave were not just inadequate, they were utterly broken. They could not account for this level of persistence, this degree of geometric order. The initial shock and awe began to give way to a desperate, exhilarating scramble for understanding. Physicists and atmospheric scientists around the world turned their attention to this single bizarre feature. They built computer simulations, they filled whiteboards with equations, they debated in conference halls, all wrestling with the same fundamental questions. How? How does a spinning ball of gas create and sustain a perfect hexagon? What deep, hidden mechanism gives it such sharp corners and straight sides? Is it a wave, resonating at a specific frequency as it propagates through the jet stream, creating 6 distinct peaks and troughs? Or is it the surface expression of something far deeper, a pattern rooted in the planet's metallic hydrogen core, projected upwards into the visible atmosphere? And perhaps the most haunting question of all, why 6? Why not 5 sides, or 7, or 8? What is it about the specific conditions on Saturn, its rotation, its wind speeds, its atmospheric composition, that so fundamentally favours the number 6? The hexagon was no longer just a scientific curiosity. It had become a challenge, a gauntlet thrown down by nature itself, daring us to comprehend the forces that could give birth to such an impossible, enduring, and beautiful monster. The age of discovery was over. The age of explanation had begun. Cassini's primary mission had already delivered a revolution, transforming Saturn from a distant point of light into a living, breathing world. We had flown through the rings, tasted the plumes of Enceladus, and gazed into the eye of the hexagon itself. We thought our time of discovery was nearing its end, that the main chapters of the story had been written. But time, as we would soon learn, was the most critical instrument of all, and we had just been granted more of it. With the primary objectives achieved, the mission was extended, then extended again, reborn as the equinox and solstice missions. This wasn't merely a victory lap. It was an opportunity for something far more profound. It was the chance to stop taking snapshots and start watching the seasons turn on a world where a single year lasts for 3 decades of our own. This gift of time would allow us to witness the slow, majestic evolution of Saturn's atmosphere, and in doing so it would completely shatter our understanding of the impossible structure at its pole. Before this, our view of the hexagon was stubbornly two-dimensional, a magnificent geometric pattern sketched across the cloud tops. We knew its width, a staggering 30,000 kilometers. We had measured the furious speed of its bounding jet stream, but we had no idea of its depth. Was it a transient meteorological curiosity, a mere film of weather floating on the surface of a vast, indifferent abyss? Or was it something more? To find out, we needed to see in ways our eyes cannot, to peel back the layers of the planet with senses tuned to the universe's hidden light. Cassini's composite infrared spectrometer, a marvel of engineering, was designed for precisely this purpose. It didn't see clouds, it sensed heat, peering through the visible haze to map the thermal structure of the atmosphere far below. As the data from these deeper layers began to stream back across 1 billion kilometers of space, a new portrait of the hexagon began to emerge, one with breathtaking, terrifying dimension. The results were unequivocal. The hexagon was not a surface feature, it was not a painted mask. What we had been observing in visible light was merely the top of an immense coherent structure, a vortex of colossal proportions that reached down and down and down. Initial readings suggested it extended at least 100 kilometers into the depths. Subsequent analysis pushed that boundary even further, to 300 kilometers or more. Imagine a hurricane on Earth, but with a vertical wall of wind extending from the stratosphere all the way down to the surface, and then continuing to plunge beneath the waves for miles. That begins to approach the scale of what we were seeing. This wasn't weather, this was planetary architecture. The 6-sided jet stream wasn't just a river of wind, it was the churning rim of a vast, solid-seeming cylinder of rotating atmosphere, an entity embedded so deeply within Saturn that it was fundamentally part of the planet's dynamic core. It was as if the planet itself had grown a crystalline gear in its own heart, and the pattern we saw was just the exposed teeth breaking the surface. This revelation changed everything. It meant the hexagon possessed an incredible, almost unbelievable degree of stability and persistence. A shallow storm can be dissipated by atmospheric turbulence, sheared apart by competing winds. But a structure this deeply rooted becomes a force of nature in its own right, an atmospheric anchor holding its position against the chaos surrounding it. It explained why the shape had remained so perfect, so constant, since Voyager first glimpsed it decades earlier. It wasn't being constantly regenerated, it was simply there, an immutable feature, less like a storm and more like a mountain range carved from wind and pressure. This profound verticality also presented a new, even more daunting puzzle. What kind of engine, buried deep within the planet's interior, could create and sustain such a monumental structure? The forces required would be titanic, originating from a place of unimaginable temperature and pressure, a place we could never hope to see directly. The hexagon was no longer just a mystery. It was the ghostly fingerprint of a process hidden in Saturn's deepest, most secret layers. With this new understanding of its depth, scientists turned their attention to its internal motion. If the outer boundary was a single, coherent entity, what was happening inside? Again, time was the key. By meticulously tracking the movement of tiny individual cloud features within the hexagon's perimeter, over months and years, a picture of organised chaos came into focus. We already knew the main jet stream, the one that forms the 6 straight sides, screamed along at over 300 miles per hour, but nested inside it, we discovered another, even faster ribbon of wind. A secondary jet racing eastward at terrifying speeds, sometimes exceeding 340 miles per hour, creating a vortex inside the larger vortex. This was a hurricane within a geometric hurricane, a maelstrom locked inside a perfectly defined cage. You could see it in the time-lapse animations compiled from thousands of Cassini images. The outer walls of the hexagon would rotate with a stately, almost rigid grace, a slow and steady cosmic waltz. But inside that perimeter, the atmosphere was a boiling cauldron. Smaller vortices would spawn, live and die, caught in the grip of the inner jet. They would swirl and dance like leaves in a whirlwind, sometimes being absorbed into the larger flow, sometimes being torn to shreds. Yet through all this internal turmoil, the 6 walls of the prison never buckled. They never wavered. The hexagon held its shape, a perfect, unwavering geometric constant against the fury it contained. It was a gravitational gyroscope, a system that maintained its angular momentum and its impossible form despite the violent energies raging within. The stability of the outer form was in stark, dramatic contrast to the pandemonium of its interior, a paradox that hinted at physical laws operating on a scale we were only just beginning to comprehend. And then, as Saturn continued its long, slow journey around the Sun, the hexagon began to change. Not in its shape, but in its colour. When Cassini first arrived in 2004, Saturn's northern hemisphere, where the hexagon resides, was locked in the deep freeze of a long winter. The pole was tilted away from the Sun, starved of its light and energy. In the images from that era, the entire region inside the hexagon was a deep, mesmerising, almost cobalt blue. It was beautiful, but also alien and cold, a vision of a world asleep under a twilight sky. Scientists hypothesized that the lack of sunlight allowed the atmosphere to clear itself. Without ultraviolet radiation to create new hazy aerosols, the existing ones slowly rained out into the depths, leaving behind a clarified atmosphere that scattered sunlight in much the same way Earth's sky does, producing a rich blue. The hexagon, acting as a barrier, seemed to prevent haze from the rest of the planet from drifting in, making this polar clearing effect even more pronounced. But as the extended mission wore on, the seasons began to turn. Spring arrived at the North Pole. Slowly, over years, sunlight began to creep back over the horizon, bathing the hexagon in continuous daylight for the first time in over a decade. And as the light returned, the colour began to shift. The deep, clear blue started to fade, replaced by a pale, yellowish tint. By the time of the solstice mission, which observed the arrival of northern summer in 2017, the transformation was complete. The hexagon was no longer blue. It had become a dull, hazy, golden brown, almost indistinguishable in colour from the rest of the planet. The sun's ultraviolet rays were once again acting as a celestial blowtorch, interacting with the methane and other hydrocarbons in the upper atmosphere. This process, known as photochemistry, was creating a thick smog of complex organic molecules, what scientists call tholins. This seasonal metamorphosis was a stunning confirmation of the hexagon's true nature. It wasn't just a dynamic barrier, it was an atmospheric container, a planetary-scale chemical beaker. For years it had protected the polar atmosphere, keeping it pristine and blue. But now, as sunlight poured in, the hexagon was trapping the newly formed aerosols, concentrating them inside its 6 walls. The golden haze couldn't escape. We were witnessing, in real time, the creation of a localized seasonal smog event contained within the most precise geometric shape in the solar system. The hexagon was an active participant in Saturn's climate. a self-contained ecosystem governed by the interplay of sunlight, chemistry, and fluid dynamics. It breathed with the seasons, changing its appearance in a cycle that takes 30 years to complete, a majestic display of planetary climatology that we were privileged to witness for the very first time. All these disparate discoveries, the staggering vertical depth, the violent internal jet, the role as a seasonal chemical barrier, were crying out for a unified theory. The old models were broken. This was clearly not a simple storm. It wasn't a chain of interacting vortices like we had once theorized. The evidence pointed to something far more fundamental, something deeply woven into the physics of rotating fluids. Scientists began to realize they weren't looking at a thing that was moving through the atmosphere, but rather a pattern that the atmosphere itself had been forced to adopt. The answer, they now believe, is a phenomenon known as a standing wave, or a Rossby wave. To understand this, you have to let go of the idea of a storm as a distinct object. Think instead of a fast-flowing river. If you place a large rock on the riverbed, the water has to flow around it. Downstream from that rock, you will often see a series of stationary ripples, waves that don't travel with the current, but instead seem to hang in place. The water is rushing through them, but the wave pattern itself is fixed relative to the rock. The hexagon, it seems, is a planetary scale version of this. Deep below the clouds, something, perhaps a thermal anomaly, perhaps a unique interaction with the planet's interior, is acting like that rock in the stream. The powerful eastward jet stream, the river of wind that eternally circles the pole, is forced to deviate around this deep, unseen disturbance. As it does, it begins to resonate. It falls into a pattern, a wave that propagates around the planet until it meets itself, locking into a stable, repeating geometric shape. This is the bathtub vortex analogy. It's not about the water draining out, but about the way a disturbance in a rotating body of fluid can organize itself. The hexagon is the visible manifestation of this deep resonance. The clouds we see are just tracers, like dust on the surface of a drum, revealing the shape of the vibration thrumming through the instrument below. It's a standing wave of immense proportions, a feature whose shape is dictated not by local weather, but by the fundamental parameters of the planet itself, its diameter, its rotation speed, its atmospheric composition, and the profile of its winds. And crucially, mathematical models of such waves show that low-number geometric shapes, squares, pentagons, hexagons, are the most stable configurations they can adopt. Suddenly, the impossible geometry began to look a little less impossible, and a little more like an inevitable consequence of physics on a grand scale. This was the pivotal turning point, the moment the mystery of the hexagon transformed. We had solved the puzzle of what it was. It was a deeply rooted, vertically massive standing wave, a pattern etched into the flow of Saturn's jet stream by a disturbance we cannot see. But in solving that, we had created a far more profound enigma. Why 6 sides? Why not 5, or 7, or 8, all of which are theoretically possible? What precisely is the nature of the unseen rock in the atmospheric river that is forcing this specific pattern to emerge? And how has this delicate balance of forces, this planetary scale resonance, remained perfectly stable, not just for the decades we've been watching, but likely for centuries, perhaps even millennia? We had peered beneath the surface, only to find that the true engine of this wonder was hidden even deeper still, in a place of crushing pressure and eternal darkness. The hexagon was no longer a storm to be observed, but a message from the abyss, and we now had to learn how to read its language. And so, the truth revealed itself not as a surface illusion, but as a structure of almost unimaginable scale and permanence. We had journeyed deep beneath the ammonia haze, past the hydrocarbon clouds, into the crushing pressures of an atmosphere thousands of kilometers thick. There we found our hexagon, not painted on the clouds, but carved into the very fabric of the planet's motion. A jet stream of colossal proportions, a river of wind wider than our own world, moving at impossible speeds. Knowing what it is, however, only deepens the enigma. It opens the door to a far more profound and difficult question. How? How does a world of seething, chaotic gas, a planet defined by its turbulence and relentless change, give birth to perfect 6-sided geometry? How does this impossible shape, this celestial stop sign, maintain its crisp, clean edges against the fury of a billion storms, holding its form not for days or years, but for centuries, perhaps even for millennia? The answer doesn't lie in a telescope, not anymore. It isn't found in the spectral data from a passing probe. To solve the riddle of Saturn's hexagon, we had to come back to Earth. We had to shrink a gas giant down to the size of a tabletop and try to build it ourselves. The quest begins in a place that looks nothing like space. It begins in a laboratory with a simple bucket of water. For decades, scientists in the field of fluid dynamics, the arcane science of how liquids and gases flow, swirl and mix, have been fascinated by the emergence of order from chaos. They knew that the universe, on grand scales, is governed by a few fundamental forces: gravity, rotation, and heat. And they suspected that somewhere within the interplay of these forces lay the secret to Saturn's impossible pattern. The experiment started simply, almost elegantly. Imagine a cylindrical tank, a miniature ocean placed on a turntable. We spin it, mimicking a planet's rotation. At the centre of this tank's base, a small heater is placed, while the outer rim is kept cool. This creates a temperature gradient just as the sun warms a planet's equator more than its poles. The spinning introduces the Coriolis effect, that ghostly force born from rotation that deflects moving objects. You have now built a toy planet, a simplified Earth or Jupiter, or perhaps, if the conditions are just right, a miniature Saturn. For years, the results were predictable and well understood. The fluid would organise itself into circular currents and swirling eddies, patterns of flow that looked much like the weather maps of our own world. Jets would form, encircling the miniature pole in smooth, continuous bands. But there was no geometry, no straight lines, no angles. The models were missing a crucial ingredient, a piece of the puzzle that was unique to the harsh realities of the outer solar system. The breakthrough came when researchers began to tweak the variables in more extreme ways, pushing their simple models to the breaking point. What if, they wondered, the speed difference between two adjacent jet streams was incredibly sharp and violent? Not a gentle gradient of wind speeds, like on Earth, but a sheer cliff, a boundary where slow-moving gas grinds directly against a hypersonic current. They adjusted their turntables, modified their fluid viscosities, and altered the heating profiles, trying to simulate the ferocious conditions near Saturn's North Pole. And then, one day, it happened. Inside the swirling water of a laboratory tank, the circular jet stream, which had been stable for hours, began to deform. It buckled. It wavered. A subtle instability began to ripple along its edge. And as the scientist watched, captivated, the circular flow snapped into a new, stable, and utterly shocking configuration. A triangle, then a square, then a pentagon. And finally, under a very specific set of rotational speeds and thermal gradients, the chaotic eddies and currents locked into place, forming a perfect six-sided hexagon. It was a ghost of Saturn, captured in a few litres of water. The sight was breathtaking, a moment of profound revelation. They had done it. They had created geometric order out of pure fluid chaos, proving that such a thing was not a violation of the laws of physics, but a natural consequence of them. The experiment demonstrated a profound principle, that when you confine a fluid jet within a very specific shear zone, with faster flows on one side and slower flows on the other, the turbulence along that boundary doesn't just create random noise. Instead, the chaotic eddies can organise themselves. They can coalesce and amplify a specific wavelength, a repeating pattern that fits perfectly around the circumference of the pole. If the conditions allow for a pattern with a wavelength that fits exactly 3 times, you get a triangle. 4 times, a square. 6 times, a hexagon. The laboratory had given us the recipe. It was a recipe written in the language of differential rotation, thermal convection, and boundary layer turbulence. But a recipe is not the same as a meal. Knowing the ingredients is one thing. Understanding how they combine on a planetary scale to create a centuries-old masterpiece is another entirely. The tabletop experiment was the first clue, the key that unlocked the door. Now, we had to scale that understanding up, from a bucket of water to a ball of hydrogen and helium 100 times larger than Earth. And for that, we need to talk about the planet's invisible heartbeat. Every rotating sphere, from a child's spinning top to a galaxy, is haunted by the Coriolis effect. It is the unseen hand that guides the currents, a consequence of living on a rotating frame of reference. On Earth, it curls our hurricanes and shapes our ocean gyres. But on Saturn, a world that spins more than twice as fast as our own and is nearly 10 times as wide, the Coriolis force is not just a guiding hand, it is a tyrannical god, a grand choreographer that dictates every single movement in the atmosphere on a colossal scale. This force, combined with the planet's temperature and pressure gradients, gives rise to one of the most important phenomena in planetary science: Rossby waves. You cannot see a Rossby wave directly, just as you cannot see gravity itself. You can only see its effects. These are not waves in the conventional sense, like ripples on a pond. They are planetary-scale meanders in a jet stream, vast undulations that snake their way through the atmosphere over thousands of kilometers. They are the planet's way of moving heat from the equator to the poles. They are the deep, slow, rhythmic breath of a world's weather engine. On Earth, Rossby waves are what create the high and low pressure systems that march across our continents, bringing us fair weather and storms. They are transient, constantly shifting and evolving as they travel. But on Saturn, something extraordinary happens. Theorists began to suspect that the hexagon was not a collection of 6 individual storms or a strange magnetic anomaly. Instead, they proposed it was the physical manifestation of a single, gargantuan Rossby wave. A wave so immense that its wavelength is precisely 1/6 of the planet's circumference at that specific latitude. Imagine a guitar string plucked and vibrating. It can vibrate in a way that produces a standing wave, a pattern with fixed points, called nodes, that do not move. Now, imagine a jet stream as a circular string wrapped around Saturn's pole. If the conditions of wind speed, temperature and Coriolis force are perfectly tuned, that string can be plucked by atmospheric turbulence. It can begin to vibrate, to undulate. And if it settles into a standing wave pattern with 6 distinct peaks and 6 troughs, the peaks of that wave would form the 6 corners of the hexagon, while the troughs would form the 6 straight sides. The jet stream isn't travelling in a hexagonal path. The hexagonal pattern is the shape of the wave that is travelling within the jet stream. It's a subtle but critical distinction. The gas itself is still flowing zonally, from west to east, at hundreds of meters per second. But the wave pattern, the geometric information, is almost stationary. It's locked in place relative to the planet's rotation, like a ghostly pattern superimposed upon a raging river. This theory was beautiful. It was elegant. It explained the geometry, the stability, and the scale of the feature. It connected the laboratory experiments to planetary physics. But it remained just that, a theory, a powerful idea sketched out with mathematics on a whiteboard. To prove it, to truly show that this was the answer, we had to move beyond the physical lab and into a virtual one. We had to build a Saturn inside a supercomputer. Modelling a planetary atmosphere is one of the most daunting computational challenges ever conceived by humanity. You're not merely simulating the weather, you're trying to recreate a world. You must begin with the fundamental laws of physics, equations for fluid motion, thermodynamics, radiative transfer, and feed them into a machine. You build a digital grid, a 3-dimensional scaffold of points encompassing the entire planet, from its core to the edge of space. At each point in that grid, you must define the conditions: the pressure, the temperature, the density, the wind velocity, the chemical composition of the gas. Then you press. The computer begins to solve the equations for each and every point, calculating how it will change over a tiny fraction of a second. It calculates how the heat from one point flows to the next, how the wind from another pushes on its neighbours, how gravity pulls everything down and rotation twists it sideways. It then takes this new state, this infinitesimally changed world, and does the entire calculation again, and again, and again, billions upon billions of calculations per second, just to simulate a few minutes of real-world time on Saturn. It is an act of digital creation, a ghost in the machine. For years, these digital Saturns failed to produce our hexagon. The models would generate jet streams, yes. They would create swirling vortices and turbulent storms. Some even produced wandering Rossby waves that would ripple around the pole before dissipating into the surrounding chaos. But nothing locked in. Nothing formed a stable, geometric shape. The virtual atmospheres were too volatile, too unruly. The models were clearly missing something vital, some stabilizing influence that existed on the real Saturn, but was absent in our digital approximation. The frustration in the scientific community was palpable. They had the laboratory evidence, they had a powerful theory, but they could not bridge the gap and make the virtual world match reality. What secret ingredient were they overlooking? The answer, it turned out, was buried deep within the data from Cassini, the very data that had confirmed the hexagon's depth. The early models had made a reasonable but ultimately flawed assumption. They had treated the jet stream as a relatively shallow feature, a fast-moving river flowing on top of a calmer, deeper atmosphere. But as we learned, the hexagon is not shallow. It is a titan, a structure extending down thousands of kilometers, far deeper than any weather system on Earth. This was the missing piece. A new generation of models was built, this time with a crucial difference. The simulations were programmed to account for a deep, powerful jet stream, one that was not just a surface feature but a fundamental part of the planet's internal rotation, reaching far down into the crushing darkness. The computers began to churn once more, processing the new physics. The virtual atmosphere began to spin up, the jet streams began to form, and as the scientists watched the data pour out, rendered into visualizations of wind and pressure, they saw it. First, a subtle meander in the polar jet. Then, the wave began to grow, to amplify. The chaotic eddies, which in previous models had destroyed any nascent pattern, were now being sheared apart by the immense momentum of the deep winds. The deep jet acted as a powerful guide, a cosmic channel that forced the Rossby wave into a stable, resonant state. The undulations sharpened, the sides flattened, and there, glowing on the screen, born from nothing more than mathematics and processing power, was the hexagon. It was stable, it persisted, it rotated at the correct speed. The model had finally worked. The virtual Saturn had given birth to its most iconic feature. It was a triumph of theoretical physics and computational power, a moment that validated decades of painstaking research. The consensus was clear. Saturn's hexagon is a deep-seated stationary Rossby wave, a standing ripple in a hypersonic jet stream, whose existence is made possible by the sheer vertical scale of the winds that contain it. It is a monument built not of rock or ice, but of fluid dynamics, rotation, and pressure. Yet, as with every great discovery, the closing of one door only reveals a dozen new ones, each leading to a deeper mystery. We now have the recipe, the fundamental physics behind the shape. But we still don't understand the nuance, the fine-tuning. Why 6 sides? Why not 5 or 7? The models show that other polygonal shapes are physically possible. What specific delicate balance of forces on Saturn favours the stability of a hexagon above all others? Is it a random outcome? A roll of the cosmic dice that happened to land on 6 when the planet first formed and cooled? Or is there some deeper, deterministic reason? Some unknown interaction with the planet's magnetic field or its internal heat engine that acts as a tuning fork, forcing the atmospheric vibration into this one specific harmonic? And what of the storm that rages at its centre? This perfect geometric border contains a swirling polar vortex of unimaginable violence, a tempest larger than any hurricane in Earth's history. The hexagon itself is a cage of uncanny order, but inside that cage is a monster of pure chaos. We have explained the cage, but now we must turn our attention to the beast that rattles its bars. We must venture past the serene straight edges of the jet stream and plunge directly into the swirling abyss of the polar storm itself. And so, having journeyed across hundreds of millions of miles, having peered through the lenses of humanity's most ambitious robotic explorers, we find ourselves face to face with the ultimate question. The Cassini mission, Our steadfast eye in the Saturnian system has given us the data, the wind speeds, the temperatures, the ethereal images of this impossible structure rotating with a godlike indifference. But data alone is not an answer. It is merely the language of the mystery. To translate it, to comprehend the forces that could sculpt a geometric titan from mere gas and wind, we must leave the physical world behind. We must venture into a universe of pure mathematics and computational power, a digital realm where we can build a planet from scratch. For the key to unlocking the hexagon lies not in a single observation, but in a virtual laboratory where we can command the winds, stir the depths, and watch, over and over again, as a world takes shape. The challenge is almost beyond comprehension. To simulate Saturn, you cannot simply create a digital sphere and paint it with bands of cream and gold. You must resurrect a world in its entirety within the silicon heart of a supercomputer. You must define the laws of physics as they operate under pressures 1,000,000 times greater than our own. You must input the planet's ferocious rotational velocity, a dizzying spin that completes a day in a little over 10 hours. You have to seed this digital world with its unique chemical cocktail, the hydrogen and the helium, the trace amounts of methane and ammonia that give it colour and character. And most crucially, you must pour into its core the primordial heat left over from its violent birth, the colossal internal engine that drives its weather from the inside out. This is not model making, it is a form of digital creationism. Scientists become the architects of a virtual Saturn, setting in motion a gravitational and atmospheric symphony, hoping that from the carefully programmed chaos, a familiar and impossible shape will emerge. The earliest of these grand simulations focused on the most obvious feature, the jet stream. We had seen it in Cassini's infrared eyes, a furious river of atmospheric gas roaring eastward at over 800 miles per hour, a colossal circumpolar highway precisely corralling the hexagon. The initial hypothesis was beautifully simple. Perhaps the hexagon was merely a wrinkle, a stable meander in this unbelievably swift current. On Earth, we see our own jet streams buckle and warp, creating the high and low pressure systems that dictate our weather. Scientists wondered if, under Saturn's unique conditions, such a meander could become so exaggerated, so perfectly regular, that it folded back on itself in 6 distinct places. They programmed their virtual atmospheres with this jet stream, a ribbon of wind at the correct latitude of 78 degrees north, and they let their digital universe evolve. The results were tantalizing yet deeply frustrating. The simulated jet stream did indeed become unstable. It developed waves, elegant and undulating patterns that rippled through the gaseous flow. It formed ovals, vast rotating storms that bore a passing resemblance to the vortices we see on other gas giants. But it never, not once, settled into the sharp, angular perfection of a hexagon. The waves would amplify and then break apart. The ovals would drift and dissipate. The virtual atmosphere refused to cooperate, stubbornly resisting the imposition of this alien geometry. It was a critical moment of insight, a realization that the answer was not to be found in a 2-dimensional river of wind flowing across the cloud tops. The models were too shallow. The secret, the ghost in this planetary machine, had to be hiding deeper. The solution, it turned out, required scientists to add a 3rd dimension to their thinking, to look not just across Saturn's face, but down into its fathomless, churning heart. Beneath the visible clouds lies a world of unimaginable pressure and temperature, an ocean of liquid metallic hydrogen where Saturn's true engine resides. This internal heat, vastly greater than the energy the planet receives from the distant sun, must escape. It does so through a process of slow, majestic convection. Imagine a pot of water gently simmering on a stove but scaled up to planetary proportions. Great plumes of hotter, lighter gas rise from the interior, while cooler, denser gas from the upper atmosphere sinks to take its place. These are not small, isolated bubbles. They are colossal convective cells, continent-sized columns of rising and falling gas that form a hidden architecture deep within the planet. This was the missing ingredient. The new generation of simulations was programmed with this vertical motion, this deep, slow breathing of the planet itself. scientists hypothesized that this internal structure could be influencing the jet stream flowing high above it, like unseen underwater mountains shaping the currents of an ocean. They watched their screens, waiting for the digital planet to reveal its secrets, and then they saw it. The models demonstrated that as the east-flowing jet stream raced over these deep convective structures, it was perturbed. The rising and falling columns of gas from below acted as invisible barriers, nudging the jet stream, deflecting its path in a subtle but relentless rhythm. The smooth flow of the current was being shaped from below, sculpted by a force it could not see but could not escape. This interaction created what are known as Rossby waves, gargantuan planetary-scale waves that are a natural consequence of fluid dynamics on a rapidly rotating sphere. We see them on Earth, but on Saturn, amplified by the planet's incredible spin and immense scale, they become something far more profound. They are the fingerprints of the planet's rotation, imprinted upon its atmosphere. The deep convection provided the initial disturbance, the pluck, on the atmospheric guitar string, and the planet's rapid rotation provided the tension and the harmonics. This combination of forces, a high-speed jet stream being rhythmically perturbed from below on a furiously spinning world, was the cradle of creation. The simulations, now running with this newfound complexity, began to paint an astonishing picture. The Rossby waves, born from the jet stream's dance with the planet's interior, began to propagate and interact. For a wide range of parameters, these waves created turbulence, chaotic swirls that would quickly tear themselves apart. But the researchers, in a painstaking process of digital alchemy, began to fine-tune the conditions in their virtual Saturn. They adjusted the depth of the convective cells. They tweaked the precise velocity profile of the jet stream. They altered the steepness of the temperature gradients between the planet's layers. They were searching for a resonant frequency, a sweet spot in the physics where the waves would not break into chaos, but would instead reinforce one another, locking into a stable, self-sustaining pattern. It was a search for a miracle of celestial mechanics, and after countless hours of processing, consuming more computational power than a small city, the miracle appeared. Out of the swirling, chaotic miasma of the simulated atmosphere, a pattern began to emerge. A subtle, six-lobed wave took shape within the jet stream. At first it was faint, a mere ghost of a shape, but as the simulation continued to run, representing months and then years of Saturnian time, the wave amplified. The peaks and troughs grew more defined, locking into place. The flow of the virtual clouds began to trace its boundary, and there, rendered in stark binary code, was the hexagon. It was a moment of profound revelation. The hexagon was not a thing in the way a hurricane is a thing. It is not a singular, solid storm. It is a wave pattern, a standing wave in the atmosphere, made visible by the clouds trapped within its geometric prison. It is the atmospheric equivalent of a Chladni plate, those simple metal sheets which, when vibrated at specific frequencies, cause sand on their surface to spontaneously arrange into beautiful, complex geometric shapes. Saturn's North Pole is a Chladni plate the size of a planet, and the hexagon is the pattern created by the deep resonant hum of its own internal engine, a planetary scale vibration made manifest. This model, the deep convection and standing Rossby wave hypothesis, represents our most complete and elegant explanation to date. It answers so many of the most perplexing questions. It explains why the hexagon is so stationary, rotating almost perfectly with the planet itself. It isn't an independent storm drifting through the atmosphere. It is anchored to the planet's deep interior, a surface expression of the planet's fundamental rotational period. It also explains the structure's incredible longevity. Unlike a conventional storm that draws its energy from a localized source and eventually dissipates, the hexagon is part of a massive, stable, self-perpetuating system. The jet stream feeds the wave, and the wave in turn helps to constrain the jet stream, creating a feedback loop that has likely sustained the pattern for centuries, perhaps even millennia. We can now look at those iconic Cassini images not as a picture of a freakish anomaly, but as a portrait of fundamental physics operating on an epic scale. Each of the 6 straight-line segments, each spanning a distance greater than the diameter of Earth, represents a region where the atmospheric flow is being guided by the invisible hand of a planetary wave. The sharp corners are not corners at all, but points where the wave pattern makes its tightest turn, forcing the clouds to follow its lead. The dark interior of the hexagon, with its relative lack of clouds, is a vast, calm, downwelling zone, the eye of a storm shaped like no other. It is a geometric ghost, a shadow cast into the upper atmosphere by the deep churning soul of the gas giant. We are witnessing a structure born not from a singular event, but from a delicate and enduring balance, a gravitational and thermodynamic waltz performed by an entire world. The ingenuity that led us here is a testament to the human mind's ability to unravel the cosmos. Unable to send a probe deep into Saturn's crushing depths, we built a Saturn of our own, a digital twin that could be dissected and tested. We used the universal language of mathematics to translate the whispers of a distant world into a coherent story. Yet, even within this triumphant explanation, new, more subtle mysteries bloom. The models are powerful, but they are not perfect. While they can successfully generate a stable hexagon under a very specific set of conditions, those same models show that under slightly different parameters, other shapes are possible. They have produced virtual atmospheres with stable pentagons, squares, and even heptagons. This begs a tantalizing question. Why 6? What is it about Saturn's specific mass, its rotational speed, its internal heat flow, and the precise latitude of its polar jet stream that makes the 6-sided solution the most stable, the one that nature chose? Is it a matter of pure chance, a roll of the cosmic dice that happened to land on a hexagon for this particular world? Or is there a deeper, as yet undiscovered physical principle that favours a 6-sided standing wave in this environment? We have found a compelling how, but we're still searching for the ultimate why. And there is the confounding issue of asymmetry. Why does this magnificent structure appear only in the north? Saturn's south pole, as we've seen, is a completely different beast. It hosts a raging circular hurricane with a distinct and terrifying eyewall, a storm more akin to what we see on Earth, albeit on an incomprehensible scale. The planet is, for the most part, a symmetrical ball of gas. Why would its two poles evolve such radically different atmospheric personalities? Does some subtle difference in the deep convection between the hemispheres prevent a southern hexagon from forming? Or could the southern pole have once hosted its own geometric marvel, a structure that has since decayed back into a more conventional vortex, offering us a glimpse into the distant future of its northern counterpart? The simulation has given us the most likely blueprint for the hexagon's construction, a towering intellectual achievement. It has transformed the hexagon from a supernatural spectacle into a predictable, if awesome, result of fluid dynamics. But it has not closed the book. Instead, it has opened a new and more profound chapter, pushing us to ask questions about planetary evolution and atmospheric stability that we hadn't even thought to consider before our journey to this ringed giant began. The grand puzzle, we are now beginning to realise, is even more intricate than we ever imagined. And so, the elegant mathematics of the laboratory finally matched the breathtaking reality orbiting nearly 1 billion miles from Earth. The puzzle box, once sealed, had been opened, revealing not a supernatural architect or a cosmic coincidence, but the exquisitely beautiful and predictable machinery of physics, operating on a scale so vast it defies our terrestrial intuition. We have charted the unseen rivers of wind that sculpt its form, and modelled the deep churning heart of the planet that sustains it. Yet, to say the mystery is solved is to miss the profound, overarching truth of this entire journey. The solution was never the destination. It was merely a gateway to a deeper, more resonant understanding of our place among these titanic worlds. Our quest to comprehend this single, mesmerizing shape has become a multi-generational human epic. A story written not in words, but in radio signals, binary code, and the tireless dedication of thousands of minds staring into the darkness, all asking the same simple, powerful question. Why? To truly appreciate what has been accomplished, you must cast your mind back. Travel with us, back to a time before the crystalline sharpness of modern imaging, back to the fleeting, grainy glimpses returned by the Voyager spacecraft. In those early portraits, the hexagon was a ghost, a geometric spectre haunting the fuzzy, butterscotch-coloured cloud tops of Saturn's North Pole. It was a scientific curiosity, so strange and unexpected that some wondered if it were merely an artifact, a trick of the light or an error in the transmission. The notion of a perfect six-sided storm, larger than the Earth itself, persisting for years, seemed to belong more to science fiction than to planetary science. It lingered in our collective consciousness as a tantalizing enigma, a single frame in a cosmic film we could not yet watch. That single frame, however, was enough. It planted a seed of obsession in a generation of scientists, a promise of something extraordinary waiting in the outer darkness, a promise that would fuel the long, arduous decades required to plan, build, and fly a worthy successor. When Cassini finally arrived, it was as if a veil had been lifted from the universe. The mission was not a fleeting flyby, but a permanent residence, a robotic emissary settling in for a 13-year tour of duty. And as it began its meticulous survey, the ghost of Voyager's photographs solidified into a stunning, undeniable reality. We saw it not as a static image, but as a living, breathing entity. We watched, mesmerized, as it changed with the seasons, its hazy winter blues slowly giving way to a brilliant golden summer hue. We witnessed colossal vortices, secondary storms the size of terrestrial hurricanes, spinning like ball bearings within its colossal boundaries, born from the sheer turbulence of its jet stream walls. We saw it all with a clarity that the pioneers of the Voyager era could have scarcely imagined. Each image, each data point, was another brushstroke in a masterpiece of atmospheric dynamics. A portrait of a storm so stable, so perfectly organised, it behaves less like weather and more like a permanent planetary feature, a mountain range made of wind. This transition, from a blurry anomaly to a high-definition dynamic system, represents more than just technological advancement. It is a testament to the enduring power of human persistence. It's a story of the scientists who dedicated their entire careers to this single mystery, who grew from graduate students poring over Voyager's initial data to seasoned principal investigators directing Cassini's gaze. They built the cathedral of our understanding brick by painstaking brick, through endless nights of computer modelling, through fierce debates in conference halls, and through the shared, communal awe of seeing a new image from Saturn appear on a screen for the very first time. They learned to speak the language of a world without solid ground, a language written in the subtle variations of temperature, pressure, and chemical composition. They were our interpreters, translating the silent, majestic dance of Saturn's atmosphere into the language of human comprehension. In their work, we find a profound lesson. The universe does not give up its secrets easily. It demands patience. It demands collaboration across decades and across borders, and it rewards that effort with moments of revelation so pure they can redefine our view of what is possible. With this newfound clarity, the hexagon transformed in our minds. It ceased to be merely a freak of nature and became what it truly is, the greatest natural laboratory for fluid dynamics in the entire solar system. On Earth, our weather is complicated, messy, and constantly disrupted by oceans and continents. Our storms are fleeting, chaotic beasts, born and dying in a matter of days or weeks. But on Saturn, a world of pure atmosphere, the rules are different. Here, the fundamental principles of fluid mechanics are laid bare, written large against the canvas of the sky. The hexagon is a pristine, almost perfect demonstration of a phenomenon known as a standing wave, or a Rossby wave, trapped in a powerful circumpolar jet. Imagine plucking a guitar string. It vibrates, but its ends remain fixed, creating a stable, resonant pattern. The hexagon is the planetary equivalent of that resonant note, a wave pattern that has found a perfect, harmonious equilibrium within the eastward flowing jet stream that contains it. The jet acts like the fixed ends of the string, corralling the wave and preventing it from dissipating into the wider atmosphere. This celestial gyroscope spinning in serene isolation offers us a unique window into the physics that governs all rotating fluids, from the water spiralling down your drain to the vast accretion disks swirling around black holes. It demonstrates, with breathtaking elegance, how small-scale turbulence and convection, bubbling up from the planet's deep, warm interior, can organise themselves into a large-scale, impossibly stable structure. The hexagon acts as an atmospheric barrier, a veritable wall of wind separating the interior of the pole from the rest of the planet. Inside this enchanted circle, haze particles accumulate differently, chemical reactions proceed at their own pace, and the entire polar environment evolves as its own distinct ecosystem. By studying this separation, we learn about the fundamental processes of atmospheric transport, discovering how energy and material are moved around on gas giants, a critical piece of the puzzle for understanding their climate and evolution over billions of years. It's a self-sustaining engine, a piece of cosmic clockwork that has likely been ticking for centuries, if not millennia, a silent monument to the organising power of physical law. And the implications of this grand laboratory extend far, far beyond the rings of Saturn. For we now live in the age of exoplanets. In the last few decades, our view of the cosmos has been revolutionised. We have discovered thousands of planets orbiting other stars, transforming them from distant points of light into potential solar systems, each with its own family of worlds. Many of these newfound planets are gas giants like Saturn, some even larger, orbiting closer to their stars in searingly hot configurations we call hot Jupiters. We will never be able to visit these worlds in person, at least not in the foreseeable future. Our knowledge of them will be gleaned entirely from the faint light that passes through or reflects off their atmospheres. We must become cosmic detectives, piecing together the nature of an entire world from the most subtle of clues. And this is where the hexagon provides us with an invaluable key, a Rosetta Stone for decoding alien skies. When we look at a distant gas giant, we are essentially trying to build a global weather map from a single point of light. It's an almost impossible task. But by understanding the complex physics at play on Saturn, we have a template. We now know that on rapidly rotating gas giants, immense, stable, and geometrically shaped patterns are not just possible. They may even be common. The hexagon teaches us that the atmospheres of these worlds might not be chaotic, uniform messes. Instead, they could be highly structured, hosting colossal long-lived vortices and powerful jet streams that create distinct climatic zones. When we analyse the spectrum of light from an exoplanet, we might see signatures of strange chemical compositions or unusual temperature gradients. Before our understanding of the hexagon, we might have struggled to explain such anomalies. But now, we can ask new questions. Could we be seeing the chemical signature of a vast trapped polar vortex similar to Saturn's? Could the periodic dimming and brightening of a distant planet be caused not by patchy clouds, but by the rotation of a giant polygonal storm into and out of our view? The hexagon, therefore, elevates our search. It encourages us to look for signs of extreme order, not just chaos in these alien atmospheres. It provides a physical basis for our most ambitious atmospheric models of these distant worlds, grounding our theories in an observed reality. Perhaps somewhere out there, a hot Saturn boasts a shimmering iridescent pentagon at its pole, or a frigid super Neptune is capped by a triangular vortex of frozen methane clouds. The strange geometry we find in our own backyard might be just one entry in a vast cosmic catalogue of atmospheric structures, each one a unique expression of the same universal laws of physics, playing out under different conditions of temperature, rotation, and composition. The storm on Saturn has given us the imagination and the scientific framework to hunt for these wonders, to see not just a planet, but a dynamic and structured world, even from light years away. Yet, even as we stand here today, basking in the glow of discovery, we must be humbled by the fact that our journey with the hexagon is far from over. Our story has been one of profound revelation, but like all great explorations, answering one question has only opened the door to a dozen more. We have a powerful theory for how the hexagon is maintained by the jet stream, but we still don't fully understand its origins. Was it born from a single cataclysmic storm deep in Saturn's past that settled into this stable configuration? Or is it continuously generated, a pattern that fades and reforms over geological timescales? And perhaps the most tantalizing question of all, how deep does it go? Our instruments could only probe the upper layers of the atmosphere. Does this incredible structure extend downwards for tens, hundreds, or even thousands of kilometres into the crushing depths of Saturn's interior? Is it merely a feature of the sunlit clouds, or is it a surface expression of a far deeper, more fundamental dynamic within the planet itself? A vast column of rotating gas anchored deep within the metallic hydrogen core. The tragic, bittersweet end of the Cassini mission means these questions will have to wait. After 13 glorious years, our eyes and ears at Saturn are now silent, having become a part of the very atmosphere they were sent to study. We are left with a treasure trove of data, an archive so vast that scientists will be mining it for decades to come, uncovering new secrets, refining their models, and building an ever clearer picture of this majestic world. But there is no substitute for being there. The next chapter in the Hexagon story awaits the next mission, the next generation of explorers who will build upon the legacy of Cassini and Voyager, armed with new technologies and new questions. They will be the ones to finally probe beneath the clouds, to measure the deep winds, and perhaps to watch the Hexagon evolve in real time over a span of decades, finally determining its true age and its ultimate fate. So, as we draw our journey to a close, we are left not with an ending, but with a profound sense of continuation. The hexagon on Saturn stands as a magnificent symbol of the universe itself. At first glance, mysterious and incomprehensible, but upon closer inspection, a place of profound order, elegance, and breathtaking beauty. It is a reminder that the cosmos is not a static backdrop, but a dynamic and ever-changing stage, filled with phenomena that will always challenge our understanding and expand our imagination. The quest to understand this one feature on one planet has taught us about our solar system, about the nature of worlds beyond our own, and most importantly about ourselves. It has shown us what we are capable of when we unite our curiosity, our ingenuity, and our unwavering desire to know what lies beyond the horizon. For every mystery we solve, the universe presents us with a new one, more subtle and more profound than the last. And in that endless, unfolding revelation, we find our truest purpose: to look up, to wonder, and to never ever stop exploring.